Every vendor with a dashboard claims a win rate. Backtests are cheap. Self-reported numbers are cheaper still. AlgoVault's live record stands at 90.3% PFE win rate across 83,480 plus verified calls. Merkle-verified on base L2. Don't trust, verify. That phrase is not marketing copy. It is a technical specification. Those numbers are anchored to a mutable on-chain state that any agent can independently verify at query time. Each call has a Merkle leaf. Each batch has a root published to base L2. Any consumer can fetch an inclusion proof and verify it against public blockchain state without trusting AlgoVault servers at all. So why does this matter? And why have most providers not done it? That is the question this video answers. The problem with unverifiable track records begins on the provider side. A vendor publishes a headline accuracy number, say 87% win rate across 12,000 calls, with no external verification mechanism. The call history lies in a database the vendor controls. Outcomes can be amended retroactively. Calls can be pruned from the published set. Backtest parameters can be tuned after the fact to fit a chosen historical window. Even providers who genuinely want to be transparent have no standard way to publish call level proof in a form that a programmatic consumer can verify without trusting the provider's API. On the consumer side, the situation is just as bad. An agent builder integrating a third-party signal has no runtime circuit breaker. If the provider's stated accuracy is overstated, stale, or cohort-specific in a way the headline obscures, the agent has no way to detect it during execution. In multi-agent architectures, one sub-agent's capital allocation depends on another sub-agent's accuracy assumption. A single bad data source propagates silently through the entire stack. Centralized raw data incumbents offer extensive historical data, but no on-chain verification layer. Their business model is subscription access to data, not falsifiable accuracy commitments. Open-source indicator aggregators deliver raw price derived numbers but no normalized directional accuracy signal. Neither category solves the core problem, a machine-readable tamper-evident proof that a specific call was made at a specific timestamp and that its stated directional outcome followed. Merkle-anchoring solves this because it makes the claim falsifiable. Publishing a route to a public L2 means any gap between the on-chain commitment and the call history returned by the API is cryptographically detectable by anyone at any time without the provider's cooperation. Here is how the anchoring works, layer by layer. Calls accumulate in a batch. Each verified call, asset ticker, direction, confidence score, entry timestamp, and PFE outcome window, is hashed using standard CA2 156-leaf construction and assembled into a Merkle tree. The Merkle root is then written to base L2, an EVM equivalent layer 2 with low transaction costs and public RPC access. Any Ethereum-compatible client can read those anchored roots without proprietary tooling. When a consumer wants to verify a specific call, the proof endpoint returns the Merkle branch connecting that call's leaf to the anchored root. The consumer verifies locally. No additional trust in AlgoVault's infrastructure required. The PFE win rate, price following efficiency, is the only public accuracy metric. It measures whether a call's directional thesis was confirmed by price action within the holding window calibrated per asset class. No survivorship filter is applied. No calls are excluded post hoc. The entire call population is committed to the Merkle tree before outcomes are resolved. The commitment precedes the outcome, and that causal ordering is what makes this tamper-evident rather than merely claimed. AlgoVault exposes this architecture through an MCP server that integrates directly into Claude Code or any MCP-compatible agent runtime. The surface is intentionally minimal. The performance summary tool reads from the public endpoint and returns the canonical accuracy phrase without requiring an API key. This is by design. AlgoVault's headline accuracy is verifiable before you purchase a subscription. An agent can confirm the live number at initialization and abort the session if it falls below a configured threshold, entirely without human review. A valid trade signal response includes a metadata block containing the call identifier, the Merkle leaf hash, and a proof URL for the inclusion branch. In a live multi-agent loop, the execution subagent reads that proof URL, fetches the Merkle branch, and verifies it against the base L2 root via a standard Ethereum call before allowing trade logic to proceed. A failed proof check halts the loop and routes to a human review queue. There is no silent failure path. 3 failure modes account for most first-time integration issues. First, dry run mode still applies to your content negotiation. An HTTP 406 response means your API key lacks coverage for the requested asset or confidence level, not a server error. Check your coverage tier in the dashboard before assuming a bug in your integration code. Second, Merkle batch lag creates a pending window. Calls are anchored in batches, not in real time. A call made during the current batch window will not have an on-chain root until the batch closes and the transaction confirms. The proof endpoint returns a pending status during this window. Implement a retry loop with exponential buck-off starting at 30 seconds. Do not treat pending as an error in circuit breaker logic. Third, coverage is 732 plus assets, comprehensive but not exhaustive. Call the asset coverage tool at agent initialization, not per signal, and cache the response for the session. A request on an uncovered asset returns a structured coverage error, never a fabricated verdict. The system only produces verdicts it can anchor. The decision to batch anchor rather than write each call to the chain individually was deliberate. per call on-chain writes at 83,480 plus call volumes would impose gas costs orders of magnitude higher, with no gain in proof strength. The live track record page exposes the current aggregate and links directly to the on-chain route for the most recent anchored batch. For regime-specific performance, each large cap calls have the longest history and the deepest Merkle coverage. Emerging layer 1s and cross. When you arbitrage pairs have higher coverage gaps during stressed market conditions, documented openly because the Merkle tree makes any gap structurally detectable regardless. The composite verdict architecture, regime classification, cross, venue signal normalization, confidence scoring, is the upstream reason the PFE rate holds across bull and bear regimes without separate backtest curves. The track record is the audit trail for those claims. The LEV track record is public, queryable without a subscription, and verifiable against base L2 state right now. Start there before evaluating anything else.